Okay, hello everyone. So welcome to the second session of the symposium. My name is Vaibhav Katewa and I'll be the host for the coming 3 talks. So after a very good first session, we have very interesting application-oriented talks in this session also. So we have 3 speakers in the session. The first speaker is Dr. Arpita Sinha from IIT Bombay. The second speaker is Dr. Uttama Lahiri from IIT Gandhinagar. And the third speaker is Sagar Patrutkar from Siemens Technology. Okay, so let's start with the first session now. So our first speaker is Dr. Arpita Sinha. She is an associate professor in systems and control, and she has been there since 2009. She received her PhD degree in aerospace engineering from ISC Bangalore in 2007. So she has a strong connection with ISC from prior graduate work. And after that, she was a postdoc at Cranfield University in the UK. And she does some very interesting work in guidance and control of multiple autonomous vehicles, path planning, consensus algorithms, and distributed decision-making systems. And today, she is going to talk about path planning and obstacle avoidance using space filling curves. So it's over to you, Dr. Arpita.
Thank you, Vaibhav. Good morning, all of you. So this is a unique experience. I don't see my speakers here anyway. So thank you very much for inviting me and giving this talk in the Psychophysical Systems Symposium. So as Vaibhav said, yes, IISc is my alma mater, and yeah, I'm very much still attached to it. So that's where I started my research on robotics. And currently, my research lies at the intersection of control systems and robotics. So in this talk, you're going to hear a lot about robotic path planning. So as the title stands, it's about application of space filling curves in coverage path planning. So these space filling curves exist in the literature of mathematics for several years. And in engineering, it has seen a lot of applications in computer science, mainly in data structure, how to store data so that it can be efficiently retrieved. There are not much work in the robotics using the space filling curves, so we thought of exploring it. So we applied the space filling curve in coverage path planning. So what is coverage path planning? So in coverage path planning, you have a region or an area. For example, this glass window here, or a region or a ground. And what is required is to visit every point in this area. So how do you plan the path of the robot so that it visits every point in this area? So what are the applications of coverage path planning? So as you can see, cleaning. So instead of this lady, if this was done by a robotic arm, how would the end effector should move? It should be some systematic way by which this glass needs to be cleaned so that you don't leave out any space or any dirty areas. In search, surveillance, inspection for this ground, you can also have applications like painting, lawn mowing, demining, or even in agriculture for spraying pesticides or seeding and so on. So what we need basically is a systematic way in which you can visit every point in a given area. Now, what are space filling curves? By definition, it is a continuous and surjective mapping from a 1D parameter interval, say 0, 1, onto a higher dimensional domain, say the unit square in 2D or the unit cube in 3D. So basically you have a curve or you have a line and you twist and turn the line to fill up a square area. Now there are various ways in which you can twist and turn, and that gives rise to different types of space filling curves. But Space filling curves also has some inherent properties by which they get this name. Okay, before coming to that, here on the right, you see some of the paths that are typically followed in order to um, do the coverage path planning in the traditional way that is available in the literature. So what we thought is, why not apply one of these curves in order to do the coverage, in order to solve the coverage problem. So we randomly picked up the Hilbert curve. So if you look at the Hilbert curve, what we have is a unit interval here, 1D, and this is the 2D. We are concerned about 2D because that's of interest to us. So what we do here is that this, in the first order Hilbert curve, we divide the interval into 4 parts and we divide the square into 4 subsquares. And then we map this to this square, the 2 to the subsquare 2, 3 to 3, and 4 to 4. So this is the first order Hilbert curve. Now, in the second order Hilbert curve, we divide this square into 4 subsquares. And we do that for each of this 4 squares, so that we get 16 squares. And we divide the interval also into 16 parts. And in each of this, we map from each of this interval here to the subsquares. And the sequence in which it is mapped gives rise to the Hilbert curve. This is the third order. So here again, this square is further subdivided into 4 more subsquares. So in effect, we have 4 to the power of 3, that is 64 subsquares and 64 intervals. So this is the third order, fourth order Hilbert curve, fifth order Hilbert curve, sixth order Hilbert curve, and so on. Now, mathematically, if the order of the Hilbert curve tends to infinity, then every point in this square will be touched by this curve. So that is why it has this name of space filling curve. Now, which curve should we pick up for the robotic application? So we pick up that particular Hilbert curve where each robot will have its footprint or sensor range. So where the sensor range can visit all the points in a given cell, we take up that particular Hilbert curve. So basically, the sensor range should match with the size of the cell, so that as it moves through this path, the entire space gets visited, or whatever action needs to be done is done by the robot. So one of the applications of this Hilbert curve was using this aerial vehicle. This aerial vehicle was supposed to do a surveillance of the ground, but not uniformly. So this region needs to be looked into more closely compared to the other regions. So the fractal nature of the Hilbert curve was utilized for, so here you are using a lower order Hilbert curve and a higher order Hilbert curve in this region, and using that you get the non-uniform aerial coverage. Now, looking at this, we thought that, well, when there's robots and there's a region, you cannot think of it without obstacles. So obstacles will exist. How will the path of the Hilbert curve needs to be changed in case it encounters a hole? So that is where our idea and our work starts. So the problem that we address here is that if there's a region which has obstacles and we do not know their locations a priori, can we find alternate paths to avoid these obstacles while ensuring that we visit every free node? We do not miss out on some nodes. And we assume that only when it comes to one of the neighboring cells, it is aware of the presence of this obstacle, not before that. And we also assume that the first and the last node of this Hilbert curve is free so that the robot can enter and exit. So this is a fair generalized idea because we know the boundary and we can find out if the corners, which are the corners that are available, and accordingly orient the Hilbert curve to start and end at the desired corners. Okay. Now, how do we solve this problem? So in order to do that, we try to explore or we try to look closer into the Hilbert curve. So if you see, the first order Hilbert curve is actually embedded into the each of the subsquares of the second order Hilbert curve. Similarly, the second order Hilbert curve is embedded in the each of the squares of the third order. They are at most rotated or reflected. So the second order is here, the second order rotated, you see here. So the same thing happens with the higher orders. Now, if you take up any higher order Hilbert curve and look closely, you see that a second order Hilbert curves are being joined in order to build up the higher order Hilbert curve. So we thought of to solve the obstacle avoidance problem for the second order Hilbert curve. The first order is too trivial because we assume that the first and the last nodes are free. So you can have an obstacle here or here, and then this is a little less obvious to solve the problem. So we picked up the second order Hilbert curve. So now we start with only one obstacle or only one node that is blocked. Now, if you see the way the Hilbert curve is moving, it is always turning 90 degrees, either to right or to left as it moves, except at node 4 and 11, where it goes straight. So if any of the node is blocked, it was supposed to go in and turn. So now if this is blocked, it can go around the obstacle or around the cell to reach NB plus 1, the node after the blocked node. Whereas if it is going straight, as in the case of this particular blocked node, here you need an intermediate node where it can jump and then go back to follow its regular Hilbert curve starting from NB plus 1. So we call this as strategy A and strategy B for our reference. So with these two strategies, we see that one blocked node in a second order Hilbert curve can be easily avoided without missing out on any points. Now, if we have to go to higher order Hilbert curves, the two second order Hilbert curves can be joined in at most these 4 ways. This is existing in the literature. So now our concern is what happens if at the exit point or the entry point of the second order Hilbert curve is blocked. So even when there are 2 Hilbert curves are joined, we see that they either go straight or they turn. So if any one of these blocks or node are blocked, then again either strategy A or strategy B would work in order to overcome the obstacle. So what is the conclusion? Given any order of the Hilbert curve, if there is only one blocked node, it can be avoided using either strategy A or strategy B. If there are more than one blocked nodes, but they are well separated, so at most they are sharing a vertex or they are not sharing anything, then the strategy A or the strategy B. So here you jump from 1 to 3, or here else you jump from 3 to 7 and 7 to 5 and then follow the regular curve. So that would work. But what if there are 2 blocks that are joined? They share a common edge. So here basically you need to jump from 9 to 12. Neither of the strategies would work. So we looked closer into 2 only two block nodes. What happens if there are only two block nodes? Say N1 and N2. Now this N1 and N2, they can either be consecutive. For example, it's here or here or here. So this is a tricky case because you have to jump from this point to this point. If the two block node satisfies this condition, from the very nature of the curve, you see that they will never share an edge. And so it's easy because we already have a strategy to evade such obstacles. If this condition is satisfied, okay, so one example is here. So the curve, this is N1 and then it goes here and this is N2. So from here, you cannot jump here. You have to visit this two and then visit these nodes. So this is a tricky one. Whereas this one, it comes here, then goes out, then gets into get into the N2 and then goes. This is easy. You can just jump here and then jump back there. So it is sometimes tricky, sometimes not. But if N1, N2 satisfies this, this would always ensure that they are well separated. Even if they are not well separated, they are sharing an edge, as in this case. But it doesn't matter because the curve goes this way. So you just use strategy A here, and then it comes back here, use strategy A here, and then it's done. So what bothers us is when they share an edge, and it is either the first case or the third case. But if you see, there are only finitely many situations that can arise here. And we have coded the evasive technique for this finitely many situations. So what did we do? We found we find a path that takes from n1 minus 1 to n1 plus 1, and then again from n2 minus 1 to n2 plus 1. And for the rest of the places, it follows the Hilbert curve. In case n1 plus 1 is same as n2 minus 1, then it has to jump from n1 minus 1 to n2 plus 1. So these techniques are tabulated here. I'll not get into the details. It's available in the paper, in the reference. So using, so if this is the n1 n2 satisfies this condition, then this is the new or evasive path that it has to follow. Using this finitely many possibilities, with that algorithm, we were able to show that a general higher order Hilbert curve with obstacles randomly spread out, but two of them can be only be sharing an edge if they are consecutive or they are within n plus 2 or n plus 3, then it is able to evade this obstacles and complete the Hilbert curve and the coverage problem. This is a hardware simulation. I'll talk about it. There's a video. Along that video, I'll talk about this one. Okay, so further from here, what if we have more than two edge connected obstacles that are coming close by along the node calculations? How do we handle this situation? So generalizing this work, generalizing to multi-agent situation, how do we use a space filling curve using multiple robots to solve the coverage problem? Another obvious thing is that the region of interest need not necessarily be a square or a rectangle. It can, in general, it can be represented as a polygon. How do we find a curve that would fit a polygon in general? Well, we have worked with Hilbert curves only. There are other curves. How would they perform. So a comparison between the different curves, a comparison with the technique that is available in the literature. So these are all that different ways this work can be extended. So this work was done by these 3 students. They are all undergraduates and they did as an in-sem project. So first it was done by Siddharth. He did the single obstacle case. It was taken up by Anand, who worked on the double and 2 obstacle case, and Maulik did the implementation. And their work, we could get this, was published in this papers. So you can look into it. So coming to the video of the hardware. So here we have used a differential drive robot and a Vicon camera for Vicon motion capture system for localization. We have not used a sensor to find the obstacles, but in the algorithm, the obstacle was given to the robot only when it comes to the neighboring cells. And using that, we have generated this space filling curve coverage, solve the coverage problem. Yeah, so now I'm open to questions.
Okay, so thank you, Dr. Arpita, for a very nice talk. So there are some questions in the questions tab. So the first question is from Aditya Jain from TCS Research. Using Hilbert curve, how is it advantageous over existing discrete path planning algorithms?
Okay, so just go back. So you see, this is something that we need to quantify, which we have not done. But for example, so there are different advantages. One is like, see, when you have to clean this glass, so the usual way of doing it is a path like this. So you may need your end effector to move all the way from the top till the bottom and then go up. Instead, it can just go around and do the work locally and then move and go to the next. It increases the height by some mean, then finish this and then go move on. So that would be helpful. So in some applications, this kind of doing it one region and then moving to the next region would be advantageous. The other advantage is as given here. So if you want to do something like non-uniformly, so you can use the fractal nature of the curve to go more finely at some region and do a more coarse coverage at some other region. So such kind of things, such kind of application, in such kind of applications, this space filling curves will be more advantageous.
Okay, thank you. The next question is from Amritesh Mehta from IISc. And the question is there any way to incorporate optimality in this scheme in terms of the path length?
Yes, so yeah, so that is the things so that is still, so the matrix by which you compare optimality in terms of energy or length of the path or such things we are still exploring, or this kind of a future work. Yeah, so I should not say we are exploring. So this is something that I have in mind. We have not done it. Currently, one of the students looking into the Sierpinski curve. Yeah, but yeah, this is something that needs to be looked into rather.
Okay. So the next question is from Srujan from BITS. Won't this process be much slower than the traditional coverage path planning algorithms? As here the robot is turning by 90 degrees many times.
Yes, so see, when you say slower, okay, so I would put it this way. So when you are doing a coverage path planning, the objective is not just to move. when it is at a particular cell, it needs to do something like either it does an inspection or it does a cleaning or it does uh, mowing or painting or something. So, and then it moves to the next square. So when you say it's slow, definitely it takes time to turn, but the objective here is not just follow the path. The objective is to do something as it goes along. So from that perspective, um, uh, you have to see how, what is the application and how does it compare between the different. Yeah, so in robotic literature, this turn, too many turns are not a good thing, but if it is a mobile robot and it is turning, is definitely questionable. But for the manipulator, when it has to do this painting or this cleaning, this might be quite useful. Like it doesn't really matter to move from right to left or go straight.
Okay. So I have many other questions, but probably I'll be able to take only a couple of those. So the
Sure.
next question is that, are there any other types of curves that could have the same property, that is level 2, 3, etc.? Or is it specific only to the Hilbert curves? This is
No,
from
so
Shishir.
all, yeah. So all space filling. So I did not explain that. All space filling curves have this property. So this is a property of the space filling curve. So as you iterate or as increase the order of the space filling curve, so it should occupy every point in the two higher dimensional space. So this is a property of all the space filling curves. The ones that I showed was like piano curve, the Hilbert curve, the Sapinsi curve. So all of them. So this is a quality that requires to qualify themselves as a space filling curve.
Okay, and the last question is, on what basis the direction of the motion can be ascertained, provided there are two or more options to move on to a subsequent cell?
No, so there are no options. So this is a deterministic path. So you don't. So Hilbert curve has to be followed. The sequence in which the cells are followed is pre-specified. So you don't have choice here. If you are following the Hilbert curve, you just follow that Hilbert curve. Now, if the question is related to the evading strategy, so we try to find out an evading strategy so that you can, so that it can be generalized for any order curve, and uh, and it doesn't need to, and it can be done online, so you don't need offline calculations. So given that, uh, so the evading path, you can make it more optimal in whatever sense you may think about, but what we try to do is something that can be online and not too much computationally intensive, and still you can cover the entire space.
Okay, so yeah, thank you again for your very interesting talk. And there are many more questions, so probably you can maybe answer them in the questions tab, or the attendees can shoot Arpita an email and she can communicate over the email.
Yes, so my
So,
email ID you can see, I've kept it here, so I'll be happy to answer whatever queries you have here.
okay, so thank you very much again, and it's a pleasure to have you here.
Thank you
And
very much.
we'll be starting the next session in a minute or so. Thank you.
Thank you.